Hello everyone, welcome back to the another session in Principles of Programming Languages. Today we will continue to learn about 4th unit. So basically you may find this 4th unit as too lengthy. Yes, it is true. If you see the syllabus of 4th unit, it is very lengthy unit, but I am sharing the probability of getting questions from each topic. From abstraction we will see one long question, from encapsulation we will see one short question, and from OOPS concepts we will expect one long question, part question. Like a question can have two parts, right? So one question you can expect from OOPS concept, the other question you can expect from ADTs. So in the same way, the concept what I am going to deal in this video is concurrency. From this area we will see one long question, one short question. The most weightage questions will come from 4th unit. So this is the area. So this area you will see most of the important questions. Right, now let us see 4.12 is about concurrency. We will be going to talk about subprogram level concurrency. So before we discuss about subprogram level concurrency, let us understand what is concurrency, how many levels of concurrencies are really existed. So what type of concurrency we will adopt for a language to understand. Now that part we will see from this video. Now, so let's understand about what is concurrency. So basically concurrency is what? Will perform more than one task simultaneously. That is what the exact meaning of concurrency. Will perform more than one task simultaneously. You can take the example of web browser. So web browser is what? Will take one task and will execute simultaneously. So it occurs basically at 4 different levels: instruction level, statement level, unit level, program level. Instruction level is what? Executing 2 or more instructions simultaneously. Statement level is what? Executing 2 or more instructions or statements simultaneously. Unit level is what? Subprograms, executing 2 or more subprograms simultaneously. Programs or executing 2 or more programs simultaneously. So in all these 3 levels, simultaneously is a common word that will execute, performing more than one task simultaneously. So it increases programming flexibility. Multiprocessor architecture speed ups the execution. So we will take to execute concurrency or to achieve concurrency, we will take multiprocessor architecture. So while you are reading the CO computer organization subject, you might have gone through with the topic of processing unit. So basically we will be having 4 kind of processing units: single instruction, single data stream; single instruction, multiple data stream; multiple instruction, single data stream; multiple instruction, multiple data stream. So as per the 4 categories what I have listed now, we are going to deal with the 2 kind of things. The 2 kind of things are what? SIMD and MIMD. So in SIMD computer, each processor has its own local memory. In MIMD computers can appear in 2 distinct configuration: distributed and shared memory systems. So we will be going to see what the languages will support concurrency. If really I have written a program, how far it executes, whether it takes single instruction multiple data stream or multiple instruction multiple data stream. Because see, there are times when we are writing a program, let's understand a small logic in the program. The reason to talk about this concurrency, because many of times we feel this is not PPL or this is maybe of operating system something. No, when we are dealing with the programming languages, we were writing the programs using programming language syntactical structure. Let's say that I am writing a program here. Now I am just writing the program which is total is equal to 1 and total plus equal to 1 and total minus equal to 1. When I have written all these 3 statements, now, so to get the exact value of total, I can know total value once after I finish all these 3 statements. So I cannot get the value here here itself or here or something, right? So we will be getting the perfect value of total once after we finish all these calculations. So it is what? We are writing a program using a programming language. We have to know how programs are being executed by the processing units. So that's what the importance of concurrency, the importance of study about the concurrency is required in PPL. So how the instructions will get executed, that part we are going to see. Now, so basically we do have two categories of concurrency. The one concurrency is what? Physical one, the other one is logical one. Physical concurrency is what? Multiple independent processor will use. That's what multiple threads of control will use. Logical concurrency is the appearance of physical concurrency is presented by time sharing one processor. Software can be designed as if there were multiple threads of control. So a thread of control in a program is the sequence of program points reached as control flows through the program. So we'll be going to see this thread of controls, or we'll be going to see a task process. So here interesting part, coroutines or what? Quasi concurrency that we were seen in the third unit last topic, a very important topic, frequent asked question, coroutine. So it is also called as quasi concurrency because we have a single thread of control to execute the coroutines. So here a program designed to have more than one thread of control said to be multi-threaded. That program is called as multi-threading program. Now let's understand about what is a task. A task or process is a program unit that can be concurrent execution with other program units of the same program. Now basically each task can support on thread of control. Task differs from ordinary subprograms in that a task may be implicitly started. When a program unit starts the execution of a task, it is necessarily suspended. When a task execution is completed, control may be returned to the caller. So tasks usually work together. So this is what a task is, what generally it's a process which is being executed in the program. Now, so we'll divide the task into two things. The process what we were executing into the program, we were dividing into two tasks. Heavyweight task, lightweight task. Heavyweight task is what? The task which gets executes in own memory space. Right, now we'll see with the help of the slide. So it takes own address space, own memory space. Lightweight is what? Same address space. And basically when we are executing in the same address space, we say it is flexible. We say it is easy to implement. So among these two, heavyweight task and lightweight task, we'll prefer lightweight task to consider or to easy to implement efficiency wise. So a task is a disjoint if it doesn't communicate with or affect the execution of any other task in the program in any way. So these are what two kind of tasks basically we'll go through in a programming language. Now when you given with a task, now how the way we'll execute that task. Now here synchronization matters. Basically synchronization is a mechanism that controls the order in which task is executed. So there should be there should be a thing, or there should be a parameter in which or by which we'll execute the task. So when we have a process to execute, we should know how that is going to execute. That's the concept is what? Synchronization. Basically we have two kinds of synchronization: cooperation synchronization, competition synchronization. It is important. As far as your end semester examinations are concerned, the topic of synchronization is important. Now, task communication is necessary for synchronization provided by shared non-local variables, parameters and message passing. Now, let's see how these two synchronizations will be happened with the example. Now, let's understand first of all what is cooperation synchronization and competition synchronization. Cooperation synchronization is what? The name itself it suggests is that two tasks will get cooperated each other. When one is doing the task in the execution part, the other one will wait. That's what cooperation, right? Competition is what? When the same variable will get shared among two, or the same two processors wanted to change one variable or one shared variable. So now we'll see. Competition is what? Two or more tasks must to use some resource that cannot be simultaneously used. True example is what? Shared counter or a shared variable. Competition is usually provided by mutual exclusive access. Now we'll see these two things with an example. So cooperation won't have any problem, correct? So let's see with the example. In cooperation synchronization, let's understand that I have two tasks. When A is getting executed, B will be cooperated and B will be waited till A completes. When B is doing the execution part, A will be cooperated and A will be quiet for some time and B will get executed. So this is what cooperation synchronization. We never face a problem with cooperation synchronization. Always the problem will come, or the deal should be done for only competition synchronization, where both the task wanted to share, or both the task wanted to update the shared variable. As long as it is a shared among two things, we have to do this thing. So that's what need for competition synchronization is highly required. Task A has a statement. Let's assume this example, total plus equal to 1, where total is a shared integer variable among two tasks. Now task A is sharing total plus equal to 1, task B also sharing. Suppose task B has the statement total into equal to 2. Let's say that total plus equal to 1, total into equal to 2. Until and unless we update this total value here in the statement, we cannot compute this value, correct? So basically total is the only variable which has to be updated. But as long as it is in the processing unit, we cannot get the value, and this total B has to be quiet till this happens. So we'll just go ahead with the cycles, how processing unit will get executed, these two things. Now if task A and task B try to change total at the same time, operation on total with the following three steps: fetch instruction, perform the operation, store back the result. Now we were taking three slots. So when we have a total value, we were just fetching the instruction here, right? Now after we fetch instruction, the second instruction will be in the wait phase. So here this is what fetching instruction, total plus equal to 1 something, and now here we will be operating it, here we will be operating it. When the operation has been started, second instruction will get fetch, right? And so while it is in operating one, here after you finish this operation phase, then only we'll come to this operation phase. So once you're done with this storing result, let's say that total plus equal to 1, initially total equal to 1. You just take that example, total equal to 1. So we were just fetching this instruction and we were performing the operation total. This instruction is what? Total is equal to total plus 1. So total initially is 1. So 1 plus 1, it is 2. So by the time we finish the operation, the total value is what? 2. So that was we got here itself 2. This is what storing the result. Storing the result. So when you operate this 2, now you can fetch this total value to complete total into equal to 2. So this is the operation for total into equal to 2. We were doing simultaneously only. So the moment when you finish here operation, we were just fetching this instruction and we were moving back. So by the time you come here, the result is available in the storing part. So this is the way how competition synchronization will do the task in the processing unit. Now, so let's understand about scheduler. Providing synchronization requires a mechanism for delaying the task execution. Task execution control is maintained by a program called scheduler. Now this scheduler is what? The name itself, it tells it schedules. It schedules the execution control. So task execution states are what? New state, ready state, running state, blocked state, dead state. This is also important. So new state is what? Created but not yet started. Ready is, it is created and it is ready to run it. Running is what? Currently in the execution. Blocked is what? Has been running but cannot now continue, unusually waiting for some event to occur. Dead is what? No longer active in any sense. So this is what scheduler maintains. So what is the current processing of task that it will be gives. So this is what phases of your task: new state, ready state, running, and blocked, dead state. So and now there are two design issues what we have to go through. Types of concurrency, we discussed about cooperation and concurrency, how and when they are created, how and when tasks start and their execution, task scheduling, methods for providing synchronization, semaphores, monitors, message passing. So we'll be going to discuss about semaphores and monitors, message passing in the next video, how these will provide synchronization. Fine. Thank you all.